In this video I'm going to run through the P1A unit for AQA Physics revision, ready for your exam. The first part of the specification talks about infrared radiation. The thing you need to know about infrared radiation is that all objects emit and absorb infrared radiation. The hotter an object is, the more infrared radiation it radiates in a given time. The next thing you need to know is that dark matte surfaces are good absorbers of infrared radiation, and they're also good emitters of infrared radiation. Whereas light shiny surfaces are poor absorbers and poor emitters of infrared radiation, but they are good at reflecting infrared radiation. So if you're asked in a question which material you should choose to be a good absorber or a good emitter, you need to choose dark and matte. If you're asking a question what's a good reflector, you need to choose light and shiny. The next thing we're going to look at is kinetic theory. Kinetic theory is a theory we use in physics, and it has two assumptions. The first assumption is that everything is made of particles. The second assumption is that those particles are free to move around, and this theory can then explain all the states of matter and the transfers between the two. So you can see we can start off with solid states of matter. Solid will, if you heat it up, will melt and become a liquid. If you continue to heat the liquid up, that will then evaporate to become a gas. If you want to cool them down, so you remove the heat, the gas will condense back to become a liquid. That process is known as condensation. And then if you continue to cool a liquid, it will freeze to become a solid. The process of freezing is also sometimes called solidification. The other state of matter change that you need to know is when a solid goes straight into a gas. The gas can also turn straight into a solid. That process is known as sublimation. So a bit of further detail with the kinetic theory is we can look at how solids, liquids and gas particles are arranged. So if we start off with a solid, you can see that the particles are in nice neat rows. They've got a really regular pattern. They're all touching. They don't really flow around each other in a solid. They've got relatively low energy compared to liquids and gases, but they are able to vibrate, and they're constantly vibrating. We can then move on to look at liquids. You can see that liquids particles are still touching each other, and that's a really important thing. Lots of students miss that out. You must remember that liquid particles touch, but the liquid particles are free to move around each other. We call that flowing. So that the liquids are fluid because they can flow. They're free to flow, and they can move over the top of each other. They don't have the same regular arrangement as solids, and they're a little bit more jumbled up, but you must remember that they're still touching. After liquids, we move to gas. Particles, the bonds between the particles and gases are completely broken. They're very separate, they're free to flow around, and there's lots of space between the atoms. And the spacing between the atoms is really important. You can notice that in solids you've got very little space, liquids you gain a little bit more space, and in gas you have the least amount of space. And just remember that liquids and gases can also be called fluids. We're going to spend a little bit of time just looking through methods of heat transfer on the next few slides. The first method of heat transfer that we're going to look at is called conduction. Okay, conduction occurs in solids, and that's one of the only states of matter where conduction does occur, and that's because the particles are very close together, so they can transfer heat energy as they vibrate and collide into one another. So as I said, this type of energy transfer is called conduction. It's the only method of heat transfer that happens in solids, and you can see by the diagram here, if we begin to heat this end of the rod, the particles inside the rod will vibrate more, and they will knock into their neighbour, and that will cause the energy transfer that way. Another way of explaining heat transfer through conduction is by a process known as free electrons. So the good conductors contain free electrons. The free electrons move through the conductor to transfer energy, and that's one of the reasons why conductors are so good at transferring energy through them. So good conductors are things like metals, and as you know, metals contain lots of free electrons. We're going to now look at a method of heat transfer through fluids. So this can happen in liquids and gases, and the main way that heat is transferred in fluids is through convection. And convection is when a fluid is heated, particles begin to move more, and they spread out. So I'm trying to get across this idea in the way that I've structured this, is that each of these areas is basically a mark in the exam. So the idea is that the particles will begin to have more energy, so they move around more. As they move around more, they spread out, and that causes the fluid to become less dense. As the fluid becomes less dense, that means that it can then rise above the more dense regions. So you get the hot part of the fluid rising, and then the more dense, cooler regions of the fluid will then start to sink to the bottom. And what begins to happen there is you get circulation. So the hotter part of the fluid begins to rise, the colder part of the fluid begins to sink, and you have a convection current. So the convection current that I've just drawn on here shows the hot air rising and then the colder air sinking to the bottom. The final method of heat transfer is the heat transfer through radiation. Okay, so the Earth is warmed from heat energy from the sun, which travels as infrared radiation or infrared waves. Because there are no particles between the sun and the Earth, that's because space is a vacuum, we can't have conduction and convection taking place, because conduction and convection rely on particles to basically transfer heat. So there's no particles in space, which is essentially a vacuum, so heat has to transfer between the sun and the Earth using a method known as infrared radiation or waves, and that's basically the infrared waves are part of the electromagnetic spectrum. They're just below visible light, and that's a method that transfers heat energy. And one thing just to remember is that the larger temperature difference between the object and the surroundings, the greater the rate of heat transfer. And that's the case for using conduction, convection and infrared radiation. One way this information can be applied is into sort of vacuum flasks. So you can see we've got a vacuum flask here. We're going to talk about the ways that a vacuum flask goes about trying to keep a drink warm or to keep a drink cold. So the first thing that you need to look at is this section here, is you've actually got a vacuum between the two layers of glass or steel, and that prevents heat loss through conduction and convection because there are no particles in the vacuum, and obviously conduction and convection rely on particles to transfer energy. So the only type of energy lost through the vacuum will be radiation. The second method to reduce heat loss we're going to look at is number 2, which is the plastic or cork lid, and that reduces heat loss because it's an insulator, so that reduces heat loss through conduction. But the main way that having a lid on a vacuum flask reduces heat loss is through convection, and that's because the convection currents can't escape, so the hot air will not be able to escape out the top of the vacuum flask, and therefore it keeps the hot air inside, or the hot fluid inside, and therefore reduces heat loss of the liquid overall. The third method we're going to look at is that the walls have silvery surfaces around the inside of the vacuum flask, so you've got a silvery surface on the inside of the vacuum flask there, and that will prevent heat loss through radiation, because as we've looked at already, silvery surfaces reflect infrared radiation, and therefore that radiation stays inside the vacuum flask, helping the drink to stay warm. The final method we're going to look at is number 4, and that's basically that glass is a poor conductor of heat. So the surrounding of the vacuum flask is a poor conductor, it's an insulator, and because it's an insulator it doesn't contain many free electrons, and therefore heat doesn't escape very easily, and there's little heat transfer taking place there. And all those 4 things combined together is one of the reasons why vacuum flasks are very good at keeping hot drinks hot and cold drinks cold. The next thing we need to look at is heat loss through evaporation, and this is basically that particles with higher energy escape from the surface of a liquid, so you can see the higher energy. The ones with slightly lower energy won't be able to escape, so they'll fall back into the liquid, and the ones with even lower energy will be somewhere down here in the liquid. So the idea is that the most energetic, the highest energy particles are the only ones that can escape, they're the only ones with enough energy to leave the liquid, and because the particles are the most energy, hottest particles leave the liquid, the average energy and temperature of the liquid decreases. So I've got a special guest to help us out here. Zach Garney from Year 11 is going to explain to you condensation.
Condensation is when a gas turns into a liquid. The rate of condensation can be increased by increasing the area of the surface or decreasing the temp of the surface, decreasing the amount of airflow over the surface.
Thank you, Zach. Thank you very much for that, Zach. So as you can see, the rate of condensation can be increased by increasing the area of the surface. It can be, the rate of evaporation works in the opposite to these things. So for condensation, you increase the area of the surface, decrease the temperature, and decrease the airflow. Whereas for evaporation, you would decrease the area of the surface, increase the temperature, and then increase the rate of airflow. So now I'm going to look at U values. U values are a measure of how good an object is at transferring heat energy. And the thing that you need to remember is that a better insulator has a lower U value. So the lower the U value, the better the insulator. This is important when you're looking at different aspects of your home and looking at ways to reduce heat loss in the home. So if you were going to choose one of the materials on this side and look at which one would be best to purchase as a way of reducing heat loss from the home, the thing that you want to be looking at is the one with the lowest U value, because that's the best insulator, and it's clearly the best one is 0.3 in terms of U value. So the roof material, 100mm insulation, would be the best of those to buy. In this next part of the video, we're going to look at payback times. So the question is, how many years would it take for each of the following energy saving devices to pay for themselves? Now this equation, which is payback time equation, is not given to you in the exam. You need to learn it. The payback time in years is equals the cost of installation in pounds divided by the savings per year in fuel costs, which is also in pounds. And that will end up giving you the payback time in years. So you've got a table here that gives you a new hot water boiler, a solar waste heater, underfloor heating, and a thermostatic radiator valves. And what we want to know is how many years it will take for these things to pay themselves back. So in each case, we're just going to do the initial cost, which is in this column here, divided by the annual savings in pounds. So you can just do a divide, and we can work out that 1,800 divided by 200 gives us 9 years. If we do this solar water heater, we're doing 2,400 divided by 100, which will give us 24 years. If we do the underfloor heating, we get 600 divided by 50, which gives us 12 years. And finally, for the radiator valves, it's 75 divided by 20, which gives us 3.75 years. So in terms of the energy saving device that will pay itself back quickest, well, that's the thermostatic radiator valves. But imagine now if I was to ask which one of those would be best to buy over a 10-year period. So which one will pay itself back after 10 years? Then what we need to do in that case is we need to work out the savings per year over 10 years, so savings times 10 minus the initial cost. So you can see that after 10 years, these two, the solar water heater and the underfloor heating, will not pay for themselves, because 10 times 100 is only 1,000, and 10 times 50 is only 500, and they're both less than the original cost. Whereas if we do 10 times 200, we get 2,000, and therefore minus 1,800 from that, the new boiler would actually save you £200. And how I worked that out was by doing 10 times 200 in brackets minus 1,800. Whereas the thermostatic radiator valves, well, they would give you, in this case, I just put this up there, 10 times 20 minus the 75, which comes out to be a saving of £125. So therefore, over a 10-year period, you can see it's more advantageous to fit the hot water boiler because it will save you more money in the long run. So now I'm going to look at heating and insulating buildings. The specific heat capacity of a material is the amount of energy required to raise 1 kilogram of the material by 1 degree C. It's really important that you get that definition absolutely perfect. So it's the energy required to raise 1 kilogram of the material by 1 degree C. It can be used to work out how much energy is needed to raise the temperature of a material by a certain amount. And there's the equation. The energy equals mass times specific capacity times temperature change. In terms of the actual equation, it would be written as E equals M times C times theta, where C is the specific heat capacity, M is your mass, and theta is the temperature change. Just following on from that equation, it would be useful to show you. I thought it'd be useful to show you the physics equation sheet. So you can see here that this is what you get in the exams for Unit 1. We get the equation that we've just looked at equals M times C times theta. That's the equation triangle for that equation. If you feel as though you need to use a triangle, remember the triangle is not given to you in the exam, but it's there in case you want to try and remember it. The other two equations that are next on the list are both for efficiency. You can see the only difference between these two is that one is about energy and the other one is about power. Remember, if you times it by 100%, then it's a percentage. If you don't times it by 100, you need to leave it as a decimal. And remember that your answer should be between 0 to 1 if it's a decimal place, or 0 to 100% if you're doing it as a percentage. The other equation that we're given, we're going to look at briefly, which is energy equals power times time. So that shows the energy used by an object depends on its power rating and the time, how long it's on for. And the final equation there is what you'll need in the Unit 1B exam, which is the velocity of a wave is equal to the frequency times the wavelength. As we look at forms of energy now, this is P1.2. There's a really useful saying that might help you remember the forms of energy, and that's most kids hate learning GCSE energy names. With this, you just take the first letter from each of those words to give you the form of energy that it refers to. So you see that for the first of all, you've got the M, which responds to the magnetic, and so on. The only one that's slightly different is that you've been given H, which stands for heat, but the best word to use there is actually thermal. So thermal is actually a better word to use rather than heat. In terms of the heat energy, thermal energy is better. Just running through where you get them from. So I've broken these down into 5 things that move, which these types of energies compared to 5s that don't really move. These are better as stores of energy. Okay, and you can see that, so light energy is the sort of stuff we get given out as light bulbs, so it travels as light photons. Thermal energy is basically heat energy, so when the temperature change. Sound energy is obviously anything that makes a noise. Electricity is the rate of flow of electrons, and is in electrical circuits, and kinetic is just movement energy. On the other side of things, we get nucleus, that's any energy that's stored inside the nucleus of an atom, and it can be broken or released when nuclear reactions take place. Elastic potential energy, that's sort of the spreading of an elastic band or pulling of an elastic band, and you get a store of energy there, or in a bungee cord. You get chemical energy, which is in things like cells or batteries, but also in any chemicals that you burn, such as fossil fuels, or releasing chemical reactions. And you've got magnetic energy, that's just energy stored by a magnetic field, so when there's a magnet around. And finally, the last one is GPE, or gravitational potential energy. That's the energy something has by virtue of its height above the ground. It's really important to know that last bit, that forms of energy are different from the energy sources. For example, solar energy is light energy, it comes from the sun, but solar energy itself is a method of generating electricity using solar as a source of light energy. Also, the idea that wind energy, or wind turbines, what they're actually using, they're not using wind, they're using the kinetic energy of the wind to turn the turbine. So looking at energy, the main reason why we study energy is for this first point here. It's one of the only reasons why we tend to study energy, and this comes straight from your specification. So energy transfers and efficiency. Energy can be transferred usefully, stored, or dissipated, but it cannot be created or destroyed. So the set amount of energy can only be transferred from one form to another, but we can't create it, nor can we destroy it. So it's conserved at all times. The second point, part B, says that when energy is transferred, only part of it may be usefully transferred. The rest is what we call wasted energy, because it doesn't do the function that we want it to. It's interesting to note that there's not really any sort of energy transfers that are 100% efficient, and we always end up with some energy being wasted. The most common types of energy that are wasted, or the most common forms of energy that are wasted, tend to be heat and sound, or thermal and sound. The final point goes on to say that wasted energy is eventually transferred to the surroundings, which become warmer. The wasted energy becomes increasingly spread out, and so becomes less useful. And that is basically the dissipation of energy to the surroundings. So if you hear that the energy is dissipated, what does that mean? Well, this is the bottom point here, that is eventually transferred to the surroundings, they become warmer, and the energy becomes increasingly spread out, and so it becomes less useful. We're just going to look at energy transfers and efficiency here. So the energy efficiency of a device can be calculated using the formula below. Remember, you can use this for energy or for power, and we can just swap power in there rather than energy. Where useful energy is measured in joules, total energy is measured in joules, and the energy efficiency doesn't have any units. It's a number between 0 and 1. Now we can turn it into a percentage just by multiplying by 100, and then you expect the number to be between 0 and 100. Okay, so if you end up calculating the efficiency of something in the exam and it's a number greater than 1 or a percentage greater than 100, you know you've done something wrong, so you need to look back over your work. Energy transfer diagrams are really useful for showing efficiency of objects and devices that transfer electricity or energy. So all the energy transfers are useful and wasted are shown for the device, and they're usually represented by something such as a Sankey diagram, which we've got examples of here. So this Sankey diagram is the Sankey diagram for a filament light bulb, and you can see that only a small fraction of a filament light bulb is released as light energy. The rest of the electrical input energy is actually converted into heat energy. So you can see that that's represented, and the thickness of the arrow sizes here and here represent the amount of electricity that's being transferred into those types of energy. If we look at the efficiency of the filament light bulb, you can see that that's around 0.1 efficiency, or 10%, and how I've worked that out is by using the useful output, which is the 10 joules, divided by the total input, which is 100. That gives me a decimal of 0.1, or a percentage by times it by 100 again of 10%. If we look beneath this one, we can see what an energy efficient light bulb's like, and we get 20 joules of energy going in, 10 joules is converted into useful output, and 10 joules is wasted as heat energy. So with that one, we can see that that is has an efficiency of 10 divided by 20, which gives us 0.5, or if you want to turn that into percentage by times by 100, we get 50% efficient there. It is usual convention to have the arrow going out to the right being the useful output, and any wasted going downwards. But that's not always the case, so don't let them catch you out on the exam by doing it a different way around. Okay, so we're just going to look at a little bit more to do with Sankey diagrams now. So there's usually, in an exam, there's sort of 3 different things you might be asked about Sankey diagrams, which I try to emphasise to you here. So the first method is when you have been given data written on the diagram. So you can see here we've got 100 joules, 10 joules, and 90 joules. And it might ask you to calculate the efficiency of the device. So again, 10 over 100 gives you 0.1. You know, if I was to change this one then slightly, so rather than having what we've got there, and if I turn it to be 200 going in there, and I told you that we were wasting 180, it might then ask you to work out the energy that comes out as useful light. So how I would do that is I would do the 200 minus 180, and that should give me the 20 joules. So the useful energy in that case would be 20 joules. And that's the sort of question that we're talking about there, where you have the data written on the diagram itself. The next question is that rather than having the data specifically written on the diagram, you've got the a number of squares shown on the diagram and one of the total energies, for example. So in this question in method 2, you can see here that we've been given that this energy input is 10 joules, but it takes up 10 squares. So how you go about doing this question is, first of all, you'd work out the energy per square, and to do that you do 10 over 20, and you can see that 10 over 20 gives you 0.5, so 1 square is equal to 0.5, and then you count the number of squares for the useful one, in case the number of squares there is 5, and so in that case you'd do 5 times the 0.5, so 5 times 0.5, which gives you 2.5 joules, and then if you wanted to, you'd be able to work out the waste energy as well by doing the 15 times 0.5 to find out what the answer is. And once you put that into your calculator, or maybe if you wanted to, you could do that in your head, you'd find that 15 times 0.5 is 7.5 joules. The third and final method would be to just use a number of squares to calculate the amount of energy. So they wouldn't necessarily give you any numbers. You could just be given the number of squares, and you would be expected to use that to calculate the energy. So in here, we're talking about the efficiency of the object. So if we know we've got 5 squares here and 20 squares there, then the efficiency of that device would be 5 divided by the 20, which gives us 0.25. If I wanted to turn that into percentage, I'd times by 100 and get 25%. So now we're going to look at transferring electrical energy. So the amount of electrical energy is that it's used by an appliance depends on its power and how long it's used for, and that gives us the equation that's on the equation sheet. Electrical energy equals power times time. Now if we wanted to work out the cost of electricity, you know, how much we're using at home, because we usually use energy with units of joules, but joules just a bit too small. Okay, we end up using too many of them. So we turn our energy into something called kilowatt hours. Now to work it out in kilowatt hours, our power needs to be in kilowatts, which are 1,000 watts. And our time needs to be converted into hours. And so we would measure our electricity in something called kilowatt hours, or kWh. So what we usually do is we work out the number of kilowatt hours we've used, and then our electricity provider provides us with a cost per unit, so how much it costs for 1 kilowatt hour. So from that we can work out our overall bill, our electricity bill, by doing the cost is equal to the number of units, the number of kilowatt hours, multiplied by the cost per kilowatt hour. And that would allow us to find out how much we're spending on electricity. Just at the end of the pre-exam now, just one final slide left. I just thought I'd go over some general science questions which might apply to all aspects of the exam. So these might come from biology, chemistry, as well as physics. So the first sort of question that's quite common on exams is, why is it important for results to be independently verified? And the answer to that question is to ensure the results are reproducible and that there is no bias. That's the classic answer that I've just pulled from a mark scheme of a past paper. Next one is sort of, what type of variables are there? So you know that the independent one is the one that you change, the dependent variable is the variable that you measure, and the control variable are all the other variables in an investigation that you have to keep the same. There are also other types of variables, continuous and categoric. Continuous variables are ones that we have in that contain a number, so it could be any value, whereas categoric are variables that fit into a specific category. Okay, and you can see here that the category here is the country, as you can see along this side, whereas going up the side we've got reserves, which is continuous. In the same way, we've got a directly proportional graph here, and in that one we've got two continuous variables. So if it's a line graph, you're using a line graph because it's got two continuous variables, whereas if it's a bar chart, you're using a bar chart because it's got a categoric and a continuous variable. When you're asked to describe a pattern that's shown on a graph, such as this one, you need to say it's directly proportional, because it's a straight line that goes through the origin. Other graphs that you tend to be asked to sort of explain it are ones that curve upwards. So it could be that you've got a graph that curves upwards, like so. And with that one, you need to sort of discuss. It might ask you to discuss how that graph's related, and to do that, you would say, well, as x, whatever variable is on the x-axis, increases, y increases. But this increase is happening at an increasing rate because it's getting faster as we go up. If the line was curved the opposite direction, you could say that as x increases, y increases, but at a decreasing rate. The final thing that we're going to look at is just what are the limitations of science. So sometimes it might ask you, like, why can't scientists do this, or why haven't they decided that they should implement this law, etc. And the sort of common themes that you could get going up with that question is they may need more data or evidence, it's not conclusive what they found out, there may be other facts involved in the investigation, or finally, that scientists aren't lawmakers, and actually we can advise, the scientific community can draw relationships and come to conclusions, but they can only advise the people that actually govern countries and make laws. I wish you luck in your P1A exam. Thank you for listening.